we'll discuss about the like structural architecture of proteins and DNA, and then we will see like basic things about crystallography. Okay, so how crystals are forming, like what are the how you will prepare the crystals, all those things. It is like very basic things, so that we will see, and then we will see some basic things about NMR. Okay, so the macromolecules, we know we have to understand the structure of the macromolecules, protein or DNA or carbohydrate, whatever it is. We have to understand the structure. Okay, so only then we can get some biological information based on the three-dimensional structure. Okay, so how big the three-dimensional structure is there, inside the three-dimensional arrangement, how big the cavity, so how many cavities are there. Okay, so each cavity can accommodate which molecule. Okay, so whether it is like it can accommodate some another protein, or it can accommodate some DNA or RNA, or it can accommodate some smaller molecules or ligands, so whatever. Okay, it depends upon the size of the cavity. Okay, so when will you know this cavity size? Only you have an idea about three-dimensional structure. Okay, so this paper basically we are going to learn about the three-dimensional structure and the techniques that are employed to find out the structure. All right. So in nature, so everywhere you have the macromolecules. Okay. So you go to the park, you will see beautiful flowers, right? You will see variety of plants. You will see variety of trees, right? You will see variety of fruits. Okay, so everywhere you see it is a protein, right? So whether it will contain like a protein or it will contain some small molecules. Okay, so both you will find the macromolecule as well as the small molecules, right? So the tree bark, it is containing like a natural these small molecules, right? You can extract the small molecules and you can try binding study with proteins, right? So you go to the park, in nature, everywhere you can see the both small molecules as well as the macromolecules. So you won't see like this any object without without presence of these molecules, right? So when was this idea like introduced, right? So know the structure, know the function. So this idea, when was it is introduced? Only very recently, just like 50 years, right? Just 50 or 60 years ago. Very recently, this idea was proposed. So previously, how people identified the disease, how they treated, or there were no treatment at all. So what was the condition like 100 years or 200 years or like 1,000 years ago? Okay, so those days they do not have any idea about the protein structure or the macromolecules, right? So they do not imagine that our body is composed of like DNA as well as like the protein molecules. We have like thousands of genes in our body, thousands of proteins, and each protein having its unique structure, and each protein behaving like behaving different function, right? They do not have any idea about like protein or nucleic acid or the structure or the enzymes or the enzymatic activity, right? The reduced activity or enhanced activity, they do not know, right? All they know is just symptoms. So based on the symptoms, right, they started treating. Only by experience, they learned the medicine, right? So they learned the medicine and it was successful. So we have like still practicing the hereditary medicine, right? We used to say folk medicine, right? Naatu marundu, right? So Naatu marundu in Tamil, folk medicine, folk treatment in English. I don't know, your regional language may have some terminology, right? So these treatment, it is passed by generation to generation. How they invented? Only by experience, right? So if they feel like a tiredness or headache or having like a high temperature in the body, right? Even smallpox, right? Smallpox, you will have like everywhere some itching, right? You will have some wound also, right? So seeing all those observations, right? So whether how first day, how what is happening, second day what is happening, whether he is taking food regularly or not, his appetite is reduced or normal, right? His motion is normal. All these things they are seeing the observation, right? Just by seeing these observation, they practiced some medicine. Okay, so they were using plants, fruits, even honey, right? Date, and then tree bark, right? They will make a special decoction, different types of decoction, different types of tree bark, different leaves. They will have like their own combination. Okay, so they made like trial and error method, and they practiced and they standardized. Okay, only thing is the quantification is not measured. Okay, now the modern medicine, the allopathy, whatever you are saying, allopathy, if you are giving like headache, what is the medicine for headache? Anybody? Come on, yeah, nobody is getting a headache, huh?
The crocin.
What?
The crocin.
Speak louder.
Sir, crocin.
Crocin. Okay, crocin. Then fever?
Paracetamol.
Paracetamol, right. So you are giving like paracetamol or whatever, right? So you will give like 500 mg or like 1000 mg, like 500 mg, 2 dose, something, right? It is like quantified, this much milligram. The allopathy it is giving this much milligram. But the folk medicine doesn't have any quantitative measures. Okay, so they will take a pinch and give it to you. That's all. Or they will give some the decoction. You take 1 glass or 2 glass, whatever. So the glass size will vary for each house. Okay, every house do not have the same glass, right? So somebody will take like a larger glass, somebody will take like smaller glass. Whatever it is, the medicine was working, right? It was working. People were get treated. They were like escaped. How did they like given this? Just by experience, and it was working without having any side effect. So those days they do not have like they didn't go for crystallography, right? Macromolecular study and PDB study, nothing. But just by seeing symptoms and they given medicine, somewhat it was like working. Okay. So only recently people started thinking about the biology, people started what is the biology is made of, right? Only very recently, only in the 19th century, people were thinking about the atom, right? So the size of the atom, right? Like last semester we saw like the story how they found what are the smaller particle. People were thinking the atom is the smallest particle, and then later on people were thinking, oh yeah, some neutron is there, proton is there, electron is there. So these are smaller size than the atom, right? So people are thinking, okay, this electron is the smallest particle. That is the like understanding like 60, 70 years ago. But later on, people were started thinking about breaking even those smaller particles, right? So that is what the CERN is doing. So they are finding Higgs boson, and now again they are finding like a smaller particle, right? So it's keep on going. It's like every day the science is advancing. So only the later the science advancement helped understanding the biology, right? So they found out like the molecules and the atom. They are making like an amino acid. So different types of amino acids are there. All these amino acids are combined together, and it is making like a long polypeptide chain. This polypeptide chain is varying from protein to protein, right? So all those things like people found only like 60, 70 years back, right? And then once they found, okay, they were thinking about how the arrangement of these polypeptide, whether these polypeptide, it is on a like a how it is on a like a linear chain, or whether it is like a folding. How do they behave, right? They were curious, and how to find out the arrangement of these polypeptides. Different trial and error method. They did like different experiment, and finally they come out with brilliant idea like X-ray can be used to find out the arrangement of these polypeptides, right? And then X-ray crystallography, the field developed. And later on, people thinking about why not NMR, right? Why not we use the UV, right? Why not we use like the IR rays? So different wavelengths, they were like experimenting. So for surprise, like each experiment given like some result, right? So they found like several observations from each like study, IR, UV, given some idea, right? So they categorize. So these like IR can be used to find out like a stretching and vibrating movement of the particles, and UV you can use for finding out the concentration of the protein or macromolecules, right? X-ray, it will give you the three-dimensional structure of the protein. So all those things, they learned only by experimenting, right? So now, they have found like how to find out the structure, right? So once they found the structure, now they started analyzing the structure, right? So in three-dimensional, how the polypeptide chain is running across, right? In between the polypeptide chain. So what are the molecules present, right? So whether any ions or water molecules or some ligands, so what can be there, right? So now they are trying to understand the binding, right? Binding capacity of like protein. So this is how the like structural biology was developing. Okay. So, do you know like which was the first structure solved by crystallography? Any idea? One, yeah.
Sir, insulin.
Insulin. Insulin, it was sequenced first. Okay.
Sir, is it myoglobin?
Yeah. So it was myoglobin and hemoglobin. Okay. So you can see the screen, right?
Yes, sir.
Yes, sir.
So hemoglobin and myoglobin was to solve the first structure, and John Kenru and Max Perus. Okay. So these people were awarded the Nobel Prize for chemistry. Okay. So this is the first time they see the protein structure three-dimensionally. All right. So before that, DNA structure also was invented. Okay, Dorothy Hodgkin. So she used X-ray to get the image of DNA. Okay, but she doesn't know. She doesn't know this is the structure of the DNA. But his mentor, taken that image to his friend. Okay, so who is that?
Watson and Crick.
Yes. So they taken that image, they interpreted that is as a DNA, and they got the name. Okay, so they were awarded Nobel Prize for finding out the DNA structure. All right. So, but later on, people realized, and Dorothy Hodgkin was given honor for that. Okay. So, just finding the structure, okay, is like a huge thing. So nowadays, if you see almost every year, that some Nobel laureate will be coming from the structural biology. All right. So you can see different way of representing the protein molecules. So this is like a space filling model, this is ball and stick model, and this is skeletal model, and this is a ribbon diagram, and this is like a surface representation. Okay, so you can represent any way, like each way it is having its own application. So ball and stick, you can see the balls representing each atom. Okay, it is proportionate with the atomic radii. Okay, atomic radii of each atom. All right. So the black one will be representing a carbon, and blue representing the nitrogen, and red representing the oxygen. Okay, and the white is hydrogen. All right. So generally, hydrogen will not be displayed. Okay. If you want to make it displaying, you can make it. All right. So this stick is representing the bond length between each atom. Okay. So if you measure the bond length, the distance between these two atoms, it will show the bond length of these two atoms. All right. So each stick, it is exactly representing the bond length of two atoms. Okay. So the skeleton model is just the bond. Okay. So usually the protein, the model will be represented as a single stick only. So if you see the peptide bond, you will see C double bond O, right? Carboxyl group. The carboxyl group is carbon and oxygen. It is connected by double bond. All right. So, but it will be displaying only one stick. Don't think it is a single bond. It is a double bond. Okay, so in protein representing whatever it is, like a double bond, single bond, it will shown as like a single stick only. But when you measure the distance, it will show exactly the double bond distance, right? So carbon, oxygen, single bond, carbon, oxygen, double bond will be having different bond length. Yes or no? Come on here. It's going to be, yes. So it's going to be like two different lengths, right? Come on, guys. Is it going to be same length or different length?
Sir, different length.
Different.
So what will be the difference? Carbon single bond will be lesser length. Carbon double bond O will be longer length. How will be?
Sir, double bond will be short.
Yeah. So double bond will be short in length. All right. So if you measure the length, you will find out. All right. So based on the length, then you can say it's a double bond. Okay. So some chemical drawing program is there. Okay. So in chemical drawing program, if you display the peptide bond, it will show you double bond. Okay, it is a chemical drawing. So the chemical drawing, it is programmed in such a way, strictly representing every bonded as appears. Okay, but protein displaying program will not show you. There are some program you can make it display. Okay, purposely if you want to show the double bond, you can make it. All right, but default it will show you single stick only. So then the cartoon diagram is there. Okay, it will represent the secondary structure of alpha helix, beta strands, and then loop. Okay, so the cartoon diagram, and then you have the surface represent. This will give you some overall idea about the global charge or global hydrophobicity, hydrophilicity. Okay, so the surface representation, by showing the surface representation, you can tell, right, like this patch belongs to neutral part. Okay, so this patch belongs to negative charge. This patch belongs to positive charge. Something you can represent globally. Okay, the charge property or hydrophobicity or hydrophilicity. Okay, so each represent the way of thinking is having its own purpose. You should learn this, right? So why you want to worry about the protein grade and structure? So as I told you already, it will help you to understand the binding pocket, binding cavity of the protein. Okay, once you know the binding cavity, you can think of a molecule which can be introduced into the cavity so that it will arrest or inhibit the protein activity or enzymatic activity. Okay, so you can think of like a drug molecule. Okay, so if you allow the drug molecule into the cavity, right, it will block the active site, so the protein will not make any function. In that case, you are stopping the like disease, something, right? So drug or inhibitor that you can design only when you learn the three-dimensional structure. Okay. Okay, so do you have any idea about this protein? This is a famous protein. You might have seen this structure everywhere. So maybe I can give, this is like a clue, this is a protease. Any idea? Okay, so it's a HIV protease, right? Okay, so so this is John Kendrew. So when the early people, they were like working, there was not like a sophisticated computer. You do not have like a graphical system to visualize the protein whatever that we are seeing today, right? So what they will do is they will make a wire, aluminum wire. Okay, so the aluminum wire they will bend it. So then they will make a three-dimensional shape of the proteins. Okay, so then they will attach this ball everywhere, and that is how they visualize the protein, right? So here I am holding can you see this?
Yes, sir.
Right. So can you see the alpha helix here? Right?
Yes, sir.
The alpha helix is running here. Right? So this side, it is showing the beta strand. Do you see that? Yes or no?
Yes, sir.
Yes, sir.
Beta strand, right? So you can see another strand that is running over here. Okay, so it's actually like insulin, a single polypeptide chain of insulin. There is another chain here. The two chain will come and it will make a global shape. Actually, this was done by last year students in practical, not last year, previous year, because last year it is like a COVID, right? So you guys also like a COVID student. You are very proud to say, we learned structural biology without going lab, right? So without even seeing the graphical system that you are learning like structural biology, right? So if you are here, right, you are luckiest person to make these kind of models, but I don't know. You have to talk to Modi ji and get the permission to come to the lab so that you will learn this, right? Okay. Anyway, at least I can show you in this online class. Very happy, right? Okay. All right. So where are we? Okay, so the people, like the early people, all right, so they were making like models like this, and they were able to study, and they did like beautiful work. Whatever that, even though we have like sophisticated facilities today, but compared to their like little bit, I feel, right? I feel like little bit we are very slow, I guess. Okay. So if you go to the PDB site, you can see the statistics, like nearly like up to today, right? Nearly like 176,000 protein structure is deposited. Okay. So you can see this dark shade. This dark shade indicates the current year deposition. Okay, so every year you can see the shade, the dark shade indicating the current year deposition. It will come around like 5 to 6,000. I think last year it is crossed around like 10,000, I guess, right? So it was like previously it was like 5 to 6,000, and then gradually it was increasing. I think it is like going up to 10,000. And this year you can see this is now just April, right? So April almost right, just like a 4,000 or something. Maybe this year also maybe we may get like a number of huge number of the person, right? So this is like the overall growth rate. These are old statistics. That's like 2017, okay, and this is again like 2018, okay. So you can see like each year, like it is the number of structures being deposited is like keep on increasing. It's a very good feeling, all right? So go to the, I would advise for doing PhD, just go to the crystallography, all right? So if you go to the crystallography, you can make like very like novel things, all right? So if you want to do, then you have to learn very basic things, right? Like amino acid properties and all those things, whatever that we are going to see. Okay. So the protein is made of like 20 different amino acids that, basically we have like 20 different amino acids that is exist in nature. Apart from this, there are like 4 or 5 amino acids that is unusual amino acids. Okay, they are not like common amino acids, and those amino acids are present in human body, but not like very, very, very rare amount. Okay. So generally, if you like a number of amino acids, it is mentioned only 20 amino acids. So different combination of these 20 amino acids make like a different proteins. Okay, and so who is dictating to a particular protein only to have like this much amino acid, right? And who is dictating like these? If you have like a combination of these 20 amino acid, you have to fold like this. You have to do this function. Who is dictating? We have no clue. All right. So the ribosome machinery, right? So it will be like picking like one by one, right? The amino acid, the tRNA will bring like one by one the amino acid. The ribosome will coin each amino acid into a long polypeptide chain, right? So who is dictating like tRNA? Okay, now you carry the alanine, go and give it to ribosome, right? Next you carry arginine, next you carry proline. Nobody knows, right? So everything is like glue. It is it's like a grinder, but it is still keep on going every day, right? It's keep on going every day. New protein is like being synthesized, and it is keep on functioning, right? So these are like open biology that you can make lot of wonder. Okay, so if you bring any new idea into this mechanism, you will be a Nobel laureate. Okay, and then next year for the new student structural biology, I have to put the Bablu is Nobel laureate. So he invented like a new thing in this field. He studied structural biology with me last year. Now he made like lot of wonder. Yes, Bablu Kumar, right? Not only for Bablu, so the chance is given equally for all the 16 students that are present here. All right. Okay. So, all right. So basically, that I was giving you like some basic things about like proteins. Okay. So maybe I will stop here. We can continue in next class. All right. So if you have like any questions, don't ask me now. Okay, you can ask me in next class because I have given only like basic things. All right. So shall we close the class? Wow, wonderful. Come on, speak, mister.
Sir.
Sir,
Sir, no, sir. I'm about to ask. There is no change in the timetable for structural biology classes, no, sir.
no change. What is happening?
Okay. No, sir. Suresh sir has changed some. I mean, has made some changes. So I'm asking you from your end.
Yeah, what change he was making?
Yes, sir. Today actually first hour is omics, proteomics and genomics. So he changed it to structural biology. So that is why I asked.
Yeah, initially this is my class, and
Okay,
last
sir.
week Suresh sir was asking me to exchange the class. I
Yes,
said
sir.
okay, and this morning he was calling me and told to take the class. That's why I'm taking.
Okay, sir. And today first hour, Thursday first hour, and Friday second hour, no, sir.
Yes.
Okay,
That
sir.
will be interchanged. Okay, maybe next week he will take the first hour. Okay, there will
Okay.
be only adjustment between me and Suresh sir. Okay,
Okay, sir.
not so much confusion with other faculties. Don't worry about other faculties.
Yes, sir.
Maybe we can exchange. Myself and Suresh sir will exchange, and we will let you know. All right.
Yes, sir. And sir,
So,
any updates regarding lab sessions, sir? For Java, she's taking lab. For
yes,
other labs also, we are.
it is structural biology. You have to come to the lab.
Uh,
Right? How can we do the online experiment?
yes, sir.
I
Because
have to
in
take the
timetable,
protein,
yeah,
right? I
yes,
have
sir.
to take the protein and I have to put in UV spectrometer. Maybe I can show you the OD in live. That's all I can do.
Oh, okay, sir.
All right?
Okay, sir.
So all of you, you should, you know, like university was thinking about calling you guys. Okay, in fact, the last the second year students, we were planning to call by January. Okay, and university was I keep on postponing. And now at the end of January we will call. Then in the beginning of February, then in the March, and then semester gone. Okay, and I don't know, like again now they started saying like the second wave is coming. This second wave, how long it will go, we do not know. But surprisingly, I should not talk about like politics. Okay, I stop here. All right. Okay, guys.
Okay, sir.
So we'll see tomorrow. All right. So have a